Okay, announcements and reminders, nothing new, nothing shocking. There's homework 5 that's due on Tuesday next week by midnight. There's also a project that's due by that day. And the homework involves implementing SVM and logistic regression. And I've had some conversations with you over the last few days, some of you. And I want to remind you that all the stuff that you do for your homework is also uh, allows you to run, you can use that for your project as well. So essentially, by doing your homework and running it on 2 different data sets, namely three different, because the homework has 2 data sets, and one for the project, you get 2 stones with, no, 2 birds with 1 stone. Any questions about homework or project? The project, I want to remind you, requires the project deadline this time requires you to may have submissions on Kaggle and also on Canvas. And the Canvas submission is going to be a little bit more involved than what you had for your previous things. Earlier, I said I just needed like a few short bullet points. This time, you're going to have something that's in prose. And don't forget to tag your Canvas Kaggle submission so that we know what your submissions are. It's just going to make our grading a little easier. Yes.
So when it comes to grading,
Uh-huh.
what are some of the things?
Good question. So there was also some conversation about this on Piazza, and I thought I would address it in class. So you're supposed to have 6 submissions on what's that thing, Kaggle. Now let's just use one of those submissions as an example. Let's say one of your submissions is Perceptron on the original data with no feature transformations. Now there are 80 some of something of you in the class, and let's say 50 of you submit a Perceptron submission, and most of you get something like 60% on it. I'm not sure what exactly those numbers would be. Let's say you get 60% on it. So I'll give you a range of, let's say, plus or minus 3%. Anything from 57 to 63 would get you full points for that submission. If your F1 scores on the private leaderboard, all of these are on the private leaderboard. If your F1 scores are way too less, that means that there's quite likely a bug in your code. So I will take away points. The further you go from the mean, the more points you lose. Similarly, if your F1 score is way too high, that seems strange. And so you'll get points for being a little too good, if that makes sense. Essentially, that means that you have not implemented the algorithm that you thought you did, because that algorithm is not going to get 80%. It's going to get only 60. So you called it Perceptron, but it was not really Perceptron. So that's the general idea of grading for each of these things. So the points for the final submission would be split across those 6 submissions plus something for your report. Does that clarify things? Some of you may have strange submissions that nobody else has submitted, so I can't really get sufficient statistics. In that case, I'll have to do the work and figure out what to expect for that. Yes.
What if we implemented a Perceptron? Because hyperparameters are like very weird.
But that's part of the process. Your hyperparameters should, your hyperparameters are to be chosen using cross-validation. If 10 people run cross-validation, the chances are you will not see very different hyperparameters among the 10 of you. So you should not have gotten weird hyperparameters. So then you lose points. Let's go in order from back to front. Yes. Yeah.
That's right. If like you said, like without feature transformation. So if you have one with feature transformation, one not to be created on separate.
Yes. Those count as separate things. Yep. Yeah.
Yeah.
Same question.
No, regarding that, so there is no option to say which feature transformation they have done on the data set. So
how will I know that? You're going to write a report that describes it.
Yeah, but like you not have anything, like not everyone would have done the same feature transformation.
Yeah, and that's absolutely right. But having done this for a few years now, turns out that more people agree on these things than not. It's quite unlikely that there would be someone who has come up with a feature transformation that is so strange that I have to run the whole thing from scratch. Yeah, but don't take that as a challenge. Other questions? Someone from not from this column. Okay, then if there are no questions, I also wanted to remind you about the final exam. It covers everything from and including learning theory. So a little bit of stuff that we did before the break, plus all the stuff that we did after the break. The good news is you'll have 2 hours for the final exam. The maybe not so, but maybe sobering news is the final exam will be like a midterm. Any questions about that? And I'll be posting something that looks like a study guide. One of us will post it, just like what I did for the midterm. There should be something, hopefully today or tomorrow. Yeah. Oh yeah, so I'm going to be, I'll be caught up with the videos till today's lecture by today. And I also realized that my office hours for next week is on Thursday, which is during the exam period. So technically, I don't have office hours next week. I'll see if I can do a special office hours on Tuesday or something. Yes.
Are we covering new material next week?
Will be technically, yes. I will not be doing a review. Yeah.
So on the exam is no calculator, no cheat sheet, right?
No calculator, no cheat sheet, no devices. All you will need is pencil or a pen and the material that we provide. It's the same sort of stuff. You will not need a calculator because most of the calculations will be easy, and it's okay if you just leave it as fragments. And I'm not going to test you on your ability to perform superhuman calculations, if that's what you're asking. Yes. Yeah.
Yeah, so there's an extra credit part of the assignment.
Yes.
But could there be some optional extra credit work that we can do kind of?
Quite likely not. Quite likely not. It's very close to the end of the semester. I don't want to open that door. In fact, the reason we have the extra credit in this homework is mostly to address the question that you had that motivated, address the thought you had that motivated the question. If there are no questions, we're going to jump back into neural networks. Today, I plan to wrap up neural networks, talk about some practical aspects, and if time permits, I'll talk about nearest neighbors. Oh, there's another question. Will the final exam have problems inspired by the homework that like the midterm? Yes. So, the homeworks are a useful study tool. Yes.
With that in mind, will homework 4 be graded? before?
Yes. Your homework for grades should be available by the weekend, and we'll also have the solutions out by then. Yes. Homework 5 will not be graded before your final, because I think my TAs will just quit on me. And that's not good for anyone. But that said, though, I do plan to make the homework 5, the theory part of it, available, the solutions for that available by Thursday next week, so that you get a little bit of time. I mean, right after the late deadline for the homework is done, you'll get the solutions.
Okay.
All right. So in the last lecture, we were talking about training neural networks. And the general idea that we kind of meandered around was the goal of learning is to minimize some sort of empirical loss on the training data. If our loss function is differentiable and our neural network is differentiable, then we can take gradients of the loss function. If we can take gradients of the loss function with respect to the parameters, then we can make gradient updates. So we can use stochastic gradient descent. So you can use an algorithm that looks something like, you iterate over the data, you pick a random example, and you say that the parameters are updated to parameters minus some learning rate. I'm using gamma here. Yes, I realized that this looks like a y. I just learned this morning that my gammas look like y's. So I'll call it gamma t if it helps, times the gradient of the loss, which is for this particular example. And if we can do this, then we can learn whatever, we can learn the weights for any neural network. The only problem is, how do we compute this gradient? And that's where the backpropagation algorithm comes along. The backpropagation algorithm is a clever algorithm that essentially says you can write down complicated functions as compositions of simpler functions. For each simple function, you can hand derive the gradients and implement the derivatives, implement those gradients. And you can use the chain rule to construct the gradient of the larger function. That's one part of backpropagation. The other part of backpropagation is that when you're applying this chain rule, you might end up with situations where you're using gradients of certain parts that have already been computed for something else. For those situations, you don't recompute the gradient, you just use the value that you computed before. So you cache any work that you did for this example. So we saw this example here where I'll just go through this one thing again, because I think this one is a little bit tedious, but worth doing. So let's say that I want to compute the gradient of the loss. So there's a loss here with respect to the ground truth. I want to compute the gradient of the loss with respect to this weight here on that edge. The loss is not directly a function of the weight, but it's a function of y. So I can apply the chain rule. The partial derivative of the loss with respect to that particular weight is the partial derivative of the loss with respect to y. Loss is directly a function of the y, so I know that particular partial derivative times partial derivative of y with respect to the weight. And now I keep recursively going down this thing. So from y, I basically traverse the path from here to here, then here to here, and then along this edge here. So at each step, I'm computing partial derivatives of just that one local function and multiplying all the partial derivatives that came along the way. And the good news is each of those pieces is small enough that you could have its partial derivative could be part of your neural network library. And so each of these partial derivatives is easy. So the partial derivative of L with respect to y is because it's regression, and we use the squared loss. So it's y minus y star is the ground truth. The partial derivative of z2, which is this node, with respect to the sigmoid, is simply the value of z2 times the value of 1 minus the value of z2. Partial derivative of the sigmoid, this quantity here with respect to the weight is just x2 because it's a linear function. And the most important point here is, let's say that just before computing that partial derivative, we computed the partial derivative on this edge. The only difference between these two edges is this last step. Everything else is common. And one of the most important lessons in computer science is if you can avoid doing something twice, you should avoid doing it twice. This computation, you don't need to perform that subtraction twice or any more than once, because you can just literally write down that value inside this node. So it'll have a little slot inside that says the partial derivative of the loss for this example with respect to y is y minus y star. So for every partial derivative, you just write it down inside that computation graph. And the next time you need the partial derivative, you just read it. So all of these intermediate steps can be cached and then reused. And a lot of the work will be done only one. Actually, all the work will be done only once. All you have to do is just keep track of the products. So, any questions? This is where we left things off at the end of the last lecture. This approach in this cartoon example here, I used a two-layer neural network with just 2 hidden units and so on. But nothing here says that it only works for 2 layers. It doesn't care. The algorithm doesn't really care about how many layers they are. You just go one step at a time and keep computing partial derivatives. And the whole process of computing the gradient essentially involves first computing what's called the forward pass, which is you compute given the current inputs, you compute the value of the loss. And when you're computing the value of the loss, you basically write down whatever values were computed along at each step. So you computed Z1, you computed Z2 and Y and the loss. You compute the loss. And then you go in the opposite direction. You basically follow the edges in all the opposite direction. You traverse the computation graph in a reverse topological order to compute the partial derivatives. And that way, by the time you hit a node, you have computed all the partial derivatives of everything that goes out of it. And that way you have all the information you need for the chain rule. Did you have a question?
Yeah, I was wondering, like if you're starting near the output, it's like the back propagation. Are technically like the weights near the end dependent or like less complex than the weights at the beginning? Because like
What is complex?
it's like dependent on less like variables or partial derivatives.
It's I don't understand. What do you mean end? Like at the what is the end here? Can you
The gradient at like Z2,
uh-huh.
that area, if you're looking back up, they would only look at the like weight. Like,
Yes. Yep.
Versus like you're looking for the gradient with respect to WH22.
Uh-huh.
You have to look at all the Z's and.
Well, not all the Z's, just Z2. Yeah. So that's true. I mean, as you go down this network, the partial derivatives accumulate more things in the product. And it turns out that's actually a cause for problems for very, very deep neural networks. Because often, but not always, like sigmoid, for instance, the output of sigmoid is a number between 0 and 1. You multiply 2 numbers between 0 and 1, you get a smaller number between 0 and 1. And imagine this, instead of 2 layers, you had 2 million layers. You're multiplying 2 million numbers between 0 and 1. The gradients at the bottom of the network essentially get closer and closer to 0. This was a problem identified in 1993, and it was called the vanishing gradient problem. And there were a whole bunch of fun solutions that have been proposed in the literature for addressing the vanishing gradient problem. You may have heard of LSTM, long short-term memory network, was explicitly proposed as a solution for that. Today, we use massive neural networks. So clearly, the vanishing gradient problem has somehow been addressed. And the way it gets addressed in transformer neural networks is through something called residual connections. I'm not going to talk about it simply because it's just too much of a detour. We can talk about it offline if you want. But you're absolutely right. Gradients that are closer to the inputs tend to be dependent on all the gradients that came about. I want to make it slightly more general, that statement, because closer to the inputs is a meaningless phrase here, because I could have a neural network that has x1 and then some value you compute here, z1. Let's say it's x1 and x2, and then you compute z2 as a function of x3 here. So it doesn't have to be closer to the input. It's more of, and let's say you have y. Maybe. It's not a question of closer to the input or not. It's a question of how many steps has this computation graph. How many steps do you need from a certain weight to the output? That the length of that chain changes what influences that gradient. And that's because of the chain rule. Yes.
Do we need to recompute the particle derivatives for every example?
Yes, that's a good point. So I said here you cache partial derivatives, right? You cache the partial derivatives for this example, and then as you need them, you just reuse the cached values. At this point, you're done with this example. You'll make a gradient update, and you're done. Then you go back, let's say you pick a new example, you have to essentially wipe out all your caches. Because it's a new example, and you have to recompute all the partial
It
derivatives.
sounds like very computation intensive for like very large neural networks.
Absolutely, yes. Training neural networks, large ones, can take days, weeks, sometimes months. And it's a huge engineering effort. There are tricks that people use for caching things along in multiple ways, but absolutely, it's true that this can be expensive. And this is about as fast as it can be without making approximations. The thing is, backpropagation has allowed us to mechanize the process of learning. Let's kind of think back about the beginning of the semester. The first learning algorithm you saw was decision trees, the ID3 algorithm. The ID3 algorithm was invented by Quinlan, and it was to learn a decision tree. And then we looked at somewhere along the line, we looked at perceptron, which was invented by Rosenblatt, and so on. Each algorithm required to learn each new concept class, you needed to invent a new learning algorithm. And then the unification across all of these was that you don't need to invent learning algorithms anymore, because instead, let's just write down the problem of learning as optimization. And then once you write the problem of learning as optimization, we can use gradient-based learning. So you're never inventing any new learning algorithms. You're just using calculus to take derivatives and optimizing a certain function, with the understanding that minimizing that loss gives you a good classifier. So we are no longer inventing learning algorithms. But then you have to take gradients, compute gradients, which is expensive. So just like stochastic gradient descent and its variants, we'll talk about that later today, are generic learning algorithms. Backpropagation is an algorithm, a generic algorithm for computing gradients. You plug them together. You don't need to invent, you don't need to really worry about your concept class being too complicated that you have to take derivatives by hand. Just give it to your library, and backpropagation computes the gradient. Plug that into stochastic gradient descent, it computes the update. So all you have to do is just define the neural network architecture and identify the loss that you want to minimize, and just throw data at the problem. Machine learning becomes ridiculously easy. Backpropagation itself is a recursive algorithm that proceeds from the top of the network down to the bottom. And I would say all modern neural network libraries implement this kind of automatic differentiation. There are a few other variants of this. In some literature, this is also called reverse mode autodiff. Reverse mode because you're proceeding backwards. What this has done is it has allowed us as a community to explore neural network architectures and come up with all sorts of crazy neural network architectures. And the creativity moves from inventing algorithms to designing neural network architectures that have interesting properties, that have all kinds of interesting properties that you think you want to come up with, that you think are important. Maybe, for instance, I'll give you some examples here. There was an explosion of something called neural Turing machines in around 2015 or 16, which was supposed to simulate a Turing machine, but in this sort of a differentiable form where you change the way the Turing machine behaves. And the reason people could use that is because of autodiff. It was a very complicated object. Transformers are an example of a success here. We don't have to keep deriving gradients by hand all the time. And that's a very freeing idea. because now you can just start thinking about your problem and what kinds of properties your problem has, and maybe invent a certain neural network just for that. Not just a neural network, also invent loss functions. The only caveat is it needs to be differentiable. And that could be a very limiting thing or not, but it's already opening up the doors to a whole bunch of interesting things. Questions? Yes,
So you mentioned it needs to be differentiable,
yes.
but in the context of SVMs, we're talking about a non-differentiable.
Sub-differentiable. It needs to be sub-differentiable. Yes. When I say differentiable, I don't know why. I've stopped saying sub-differentiable. I just imply sub-differentiable, but I should be careful with that. You're right. Sub-differentiable. There is a line of work on, there is a interesting research exploration of what happens if you have non-differentiable pieces inside. That makes life very, very interesting. And now you can't use this machinery out of the box. So you have to do all sorts of other things. I'll talk about that offline if you're interested, because I find that fascinating. But just, yes.
So in the example, like, it's easy to us to think about, like, we're taking up derivative of equations, but how the libraries like are doing it.
They work with computation graphs. The whole abstraction internally is a computation graph. PyTorch builds, as you are writing, as it goes through your code, at every step when it's interpreting your code, it's actually constructing the computation graph on the fly. And then when you say loss, when you construct a loss, it just creates a computation graph for the loss. And when you say loss.backward, which is how you invoke backpropagation, it essentially goes through that computation graph that it has built internally in the reverse order. So it's constructing these computation graphs. It looks like you're writing, you might be writing A equals B plus C, and it looks like you're adding B and C to produce A. But what's happening internally is a node called plus is created, which has values B, which has arguments B and C. So this graph is created internally. And at the same time, the value is computed and stored inside this. So the forward pass is when executing that line is constructing the graph and computing the value simultaneously, so that then I can say A dot backward. And that will take partial derivatives of that with respect to B and C. It's a very, very well-written abstraction that hides a lot of the complexity from you. Okay, but the important point is everything is operating inside this sort of thing. This is almost like a standard scaffolding for most usages of most of the ways in which neural networks are trained look like this. You iterate over the data, you shuffle the data. These days you don't even have to shuffle the data. The libraries take care of that internally. You iterate over a training example. There's a small catch there, which we'll talk about briefly. You compute the loss on that example, and then you compute the gradient using backpropagation, and then you make an update. You do this for sufficiently long number of times. It doesn't really matter whether your parameters are defining a linear classifier or a multi-layer network or something much, much more complicated. This algorithm essentially looks very similar. Yes.
For neural networks, does it make a difference how we initialize our weights? Because I know, like, for, what was it, SVM and logistic regression, it did make a difference how we initialized our weights?
It did not. For SVM and logistic regression, it does not make a difference how you initialize your weights. For a neural network, it absolutely does, because the optimization landscape might have multiple local minima. For logistic regression, for SVM, for perceptron, the objective that you're optimizing is convex. There's no such guarantee here. You might have something like this. If you initialize at this point, you might end up here. If you initialize here, you might end up here. And if you're very, very unlucky, you initialize somewhere here, you might actually end up in a saddle point, which is like the worst of all worlds. The gradient is 0, but it's not even a local minimum. But that doesn't happen too often. Yeah, go on.
Is there then an ideal sort of way to initialize our weights for a network? Or is it dependent on the, like, the data that we have?
I would push back on the word ideal. There is folk knowledge. We have good initializers that have proven to be useful in the literature because people have tried out different types of initialization. There is one kind of an initialization, I'll name it here. Basically inside this place, there's one initialization that's called the Xavier initialization, which is these days the default. And it initializes from a normal distribution whose parameters depend on the number of incoming edges and the number of outgoing edges and such things. And Xavier initialization, if you use a library like PyTorch, I think you don't even have to say that you want to use it because this is the default. But there are others as well. And it makes a huge difference. If you initialize incorrectly, then you're host. Which is kind of annoying if you think about it, because if training takes 3 months, and then after 3 months you find out that, oh, your initialization was not great. And this is an expensive exercise computationally. And this is where the energy requirements of training start mattering. Meaning the actual amount of electricity consumed by a data center for training large language models is non-negligible. All right, I think we're kind of going away from the details of the algorithm into something that is more practical. So let's actually get into that head on. So we've seen what neural networks are. We've seen how to make predictions with it. That's just the forward pass. We've seen how to train the parameters of a neural network. And the answer is you use gradient-based optimization and you use backpropagation to compute gradients. People don't say that with those many words these days. People just say we use backpropagation for training. Or in fact, people don't even say that. They just say we used a certain algorithm and all the other stuff is taken as given. So now let's talk about practical issues for training and building neural networks. The first point is what we just discussed. There is no guarantee of convergence. Your parameters, if your neural network architecture and your loss is unkind in a certain way, your parameters might end up oscillating without ever getting to some sort of a minimum. Or it might at best converge only to a local minimum. This can be a problem because in practice, neural networks are trained on massive amounts of data, which means we have maybe thousands of epochs. At this point, we don't talk about epochs, we talk about updates, the number of updates that you make. Thousands and millions of updates might be needed, and this might require many hours, many days, or even months of, I say CPU or GPU time, mostly just GPU time, but you can't actually get to your GPU without a CPU. There are actually specialized hardware that have been invented to facilitate this sort of training. There's a device called Cerebras. There's a device, Google has something called the TPU, Tensor Processing Unit. These things are designed to help facilitate training these kinds of models. And a question that is never particularly clear is, how long should you train this model? How many updates do you need? And depending on the application, you can think of it as, you can choose the number of epochs, you can choose, you can track the error on the training data, or actually the loss on the training data, like you're doing for your homework. And you decide that training is done when that curve starts flattening out. Or you could actually keep track of error on a held out data set. And you basically, after every bunch of updates, you measure the error. And if the error starts increasing, you decide that training is done. And this requires a fair amount of infrastructure to make sure that you are actually measuring those errors. You're checkpointing your models along the way, saving all the things, so that once you decide that your training was, let's say you are currently in update number 12,000. And using some heuristic, you decide that the model after update number 11,000 was the best one. You can't go back and run those 11,000 updates again. You better have saved the model, because otherwise you've lost a whole bunch of compute time. There are a few techniques for avoiding local minima, but really this is not avoidable. One answer is that it's worth always, anytime you have experiments with neural networks, it's worth restarting with or redoing training with multiple initializations, which is equivalent to these days essentially setting the random seed, because all the parameters are initialized randomly. So you choose multiple random seeds and train the models. And now you get multiple models. You can do a few things. You can evaluate all of them. And if all of them perform similarly, then you have some sort of, you can proclaim that your whatever you're training is stable to the choice of random seed. Or you could do something even more. You could actually treat them all as different models, and you can have them all vote on the final label. So you could build like a cheap ensemble that way. Questions? Another thing that's worth, another practical issue involves something called a mini batch. Let's kind of let's think about stochastic gradient descent again. The way I explained it is, you pick one random example, you pretend that that example is your entire data set, you take the gradient and you make an update. Why should you pretend that one example is the entire data set? Why not 2? Why not 10? Why not a small batch of examples? It's not the entire set of examples. You randomly pick 10 examples maybe, and then you pretend that that is your entire data set, and you write down the loss on that, and you take the gradient. This idea is called using, this is the idea of using a mini batch. You pick a set of examples, a random set of examples, and you pretend that that set of examples is your entire data. You write down the loss functions, you compute the gradient, and you proceed exactly as it was before. Now, the way in practice, the way it is implemented is your training loop changes slightly. Your training loop doesn't iterate over individual examples, but it iterates over mini batches. So you shuffle the data, and then you take the first mini batch, treat it as the data set, make a gradient update. Then you take the second mini batch, third mini batch, and so on, till you run out of mini batches, and then you go back to the top. And each mini batch gives you an update. When I said, we talk about a certain number of updates, that's what I meant. How many mini batches do you use? Or how many examples do you use in a mini batch? Well, that's another hyperparameter. One thing that we get very, very comfortable with neural networks is we collect a lot of hyperparameters. Let's just keep track of how many we've had so far. The architecture of the network, which is the depth, the width, the number of the activation function. All of these are design choices. When we are doing gradient-based optimization, we have the initial learning rate. We also have the learning rate schedule, the choice of how do we decrease the learning rate. The number of epochs, the convergence criteria. Now we have a new one, the size of the mini batch. By the end of the next 15 minutes, I think I'll probably introduce you to 5 or 6 more hyperparameters. And we'll talk about that problem later. Yes.
Does the if we're using mini batch instead of a single example, how does that affect our batch propagation process?
It doesn't change a thing. I'll tell you why. I'll tell you why in a minute. I'll tell you, before I talk about what changes in batch propagation, I'll tell you what mini batches does for you. The key idea of stochastic gradient descent is that we want to compute the gradient of the full loss function. And that is expensive to compute. So we have a stochastic estimate of the loss of the gradient. If you use a mini batch, then your stochastic estimate becomes better. So this leads to more stable optimization. Larger mini batches lead to more stable optimization. But if your mini batch gets really, really large, then you're back to the original problem. You have to take a whole bunch of gradients before you take a single step. So there's a sweet spot. What mini batches do is that they give you, they make the process of convergence a little faster. And the size of a mini batch depends on how much memory you have in your GPU. Really, that's what it often comes down to. But now the question that you asked, how does stochastic gradient descent change? Let's think about it. Suppose I have, let's say I have a mini batch of size 8, and I have a loss of some neural network of some example xi. Oh no. So I have the loss, and this is, let's say, I equals 1 to 8. What did we know about backpropagation? We knew that, let's kind of work inside out. The neural network was a differentiable function. The loss is a differentiable function. So I can compute the derivative of the loss using backpropagation. Summation is also differentiable. So I can literally compute this gradient with respect to the weights using backprop. So the loss for using the notation that, or a notation that looks a bit like your code, you might say the loss for this mini batch is this summation, and I can say loss dot backward. And the reason this works is because the summation is a differentiable function. So the loss is a number, I can take the gradient of that with respect to all the parameters. That's it, nothing changes. The reason this works is because adding a bunch of differentiable functions gives you a differentiable function. Does that?
This mini batch, well, because there are, you will do fewer steps, so it will reduce training time.
It may not, because this allows, not really. It just makes training a little bit more stable, but not really. There's a question on Zoom, I'll come to that in a minute. It does not really reduce training time because you may be able to converge a little faster. You could choose to stop a little earlier, but in practice, what I have seen is that we end up making our models bigger. We end up making our data bigger. And so we start getting more ambitious, and so we end up taking more time because our problems get bigger. You can do more work or slightly better in the same amount of time. The question on Zoom is super interesting. If the neural network can get stuck in local minimum, how can we guarantee reproducibility? Based on my experience, multiple neural networks tend to make similar predictions, which suggest that they learn the same thing. Does this mean that for the most part, the loss functions we minimize have local minima that are approximately global? This is such a fascinating question. Let me draw a picture here because so I'm going to draw a cartoon example of a loss. So let's say these are all the weights of the neural network are in this thing we are looking at, and this is the loss. And this line here represents maybe a million dimensional vector, all the weights together. And maybe the loss surface might look something like this. Now, let's say that you start here and you end up at this place. You start here, you end up here, you start here, you end up here. And let's say this is here. So there are 1, 2, 3, and 4 different local minima here. And depending on where you start, you might end up in one of those 4 places. It seems like 1, 2, and 4 are kind of similar as far as the loss value goes. And maybe 3 is not that great. And this is the observation that's being made in this comment. Often what happens is, at least with a lot of modern neural networks, the largest ones, when we train on a lot of data, the variation across initialization does not seem to matter so much. because maybe the loss values are kind of similar at convergence. There may be occasional bad local minima like this number 3 here, but that doesn't seem to happen all the time. So this is something that we do not understand yet. This is because we're talking about a very high dimensional space here. That said, I have encountered situations where changing the initialization can change the performance all the way from it can give like a 10% difference in performance, but that doesn't happen all that often. It happens, but not all that often, which suggests that the loss landscape has these patches of flatness with respect to the minima that are all kind of similar, and maybe the choice of the initialization matters less than the other randomness that exists in the process, like the choice of your data and the architecture and such things. Those contribute far more to the performance than merely the initialization. It's completely an empirical observation. I don't think we have evidence that the local minima are approximately global because we actually have no idea what the global minima are. But this is a direction for open exploration, or an open question for exploration. Okay, we've talked about mini batches. Let's talk about another practical aspect, which is all the various tricks that exist about involving gradients. We've seen simple gradient descent. Let's say that you have an example or maybe a mini batch, and I can compute the gradient of the current mini batch, and I can call it GI. And all of the algorithms we saw essentially have the same form. Parameters are set to parameters minus a learning rate times the gradient. This is stochastic gradient descent at its very core. But it turns out that doing just this can actually hurt, not hurt. In theory, this is all you need. In theory, this will converge to the local minimum if you run this for long enough. But in practice, let's say your landscape, your optimization landscape looks something like this. Along one dimension, there is very little, along the vertical dimension, the function converges really, really fast. Along this dimension, it's very, very flat. So does this picture make sense? Now, let's say you start somewhere here, and the gradient, because the function converges very fast in one direction, takes you down that hill, and then it keeps zigzagging all the way through. Eventually, this will take you to the minimum. But you can see that this is not the greatest path. Maybe if you had done something like this, that would be a little faster instead of zigzagging. This was the observation that motivated an algorithm in 2010 or 11 called ADAGRAD. The observation is that when the gradients change very, very fast, that could make learning unstable. And the quality of the model could change quite a bit depending on when you stop the learning. So the number of epochs suddenly becomes super important. And the reason for this problem is because the optimization landscape has this sort of an ellipsoidal shape, where one dimension matters a lot more than the other. And this is just 2 dimensions. In practice, we have millions of them. Maybe some dimensions matter a lot more. The function drops very steeply along that. Along some other direction, the function doesn't drop that fast. And there are a few different tricks here. I'll talk about ADAGRAD briefly after this, but one idea to address this is called momentum. So the original gradient descent was parameters should be set to minus the learning rate. This time I'm using eta instead of gamma. I'm not sure why. Times the gradient. G is always the gradient here. This means that the only gradient that matters for the update is the gradient that you compute for the current mini batch. All the previous gradients are tossed out. What momentum says is Instead of that, why not just keep track of a moving average of gradients? So you have V, which is a moving average of the gradients that you've accumulated so far. And when you compute the new gradient, you add it to the moving average, but you don't add all of it. So maybe it's something like you have 0.9 times the previous moving average plus your learning rate times the current gradient. So you take a little bit, maybe it could be 0.9, it could be 0.1, it's a hyperparameter. You take a little bit of the previous gradient and add the current gradient to it. But this is not the previous gradient. This was like this VT itself is the average of the previous gradient and the history. So VT capture is like a exponentially decaying moving average of the entire history of updates. And then instead of updating the parameters with the gradient in the direction of the gradient, you update it in the direction of this smoothed term. This essentially serves to smooth the gradients. And this allows you to, it basically makes this thing a little smoother. This is called momentum. And now we have essentially we are updating, the update is no longer the gradient, but it's the moving average of the previous update and the current gradient. And we have a new hyperparameter, mu. Mu controls how much of the previous gradient should live in the current update. So here mu, often a common value of mu that I've seen is 0.9. Don't ask me why. It's there. It essentially, momentum serves to smooth the updates, and it leads to a little bit of stability with the training process. Questions? The reason it's called momentum is because when it was first introduced, there was this sort of a physics-based analogy here. I have forgotten what it was, but you can look it up.
Deep learning frameworks support these kind of things.
Yes, they do. In fact, there are a whole library of optimizers, and you just change the class name. You create an optimizer that called whatever the name is, and you get all those tricks. But we're not even done. This is just the first trick. I talked about AdaGrad. So far, what we saw was there's a single learning rate that applies to all the parameters, right? GI is actually a collection of parameters. All the parameters get the same step size. Why should that happen? Maybe different parameters should get different step sizes. Maybe parameters that are changing, or so maybe features or things. This is easiest explained with a linear classifier. Features that change very, very fast or very often should get smaller step sizes. Features that don't change much or don't occur often with non-zero values should get larger step sizes. And that's the idea of AdaGrad. So we're still, this is orthogonal to gradient, to momentum. We're still back to parameters is parameters minus the gradient. But here we have an index I here, which is the ith parameter. So what we get is the ith parameter gets its own learning rate, which is some learning rate, initial learning rate, eta plus a constant alpha plus root of ci. This is for the ith. This is the learning rate for the ith parameter. And the only question is, what is the ci? Ci is simply the accumulated updates, the square updates to this particular feature. So there is a certain weight, wi, this is parameter I, and the gradient for that particular parameter is gi for this many batch. For the previous one, it will be gi t minus 1, gi t minus 2, and so on. This expression here is simply adding up all the squares of the gradient. The intuition is, imagine what happens if there is a certain parameter w that gets massive updates. then GI is really large, GI square is really large. That means this sum C becomes really large. Because C is in the denominator, this quantity becomes very small. A parameter that has been updated a lot, the learning rate for that gets very, very small. So parameters that get large updates get increasingly smaller updates going ahead. Parameters that are rarely updated get larger updates because Ci will be small. And this has another sort of a stabilizing effect on learning. It's called ADAGRAD. ADAGRAD is short for adaptive gradient. And you don't have to worry about implementing this because it's kind of tedious, but more importantly, your libraries do it for you. There's another variant called RMS prop. RMS prop is very, very similar to ADAGRAD, except this C itself is rather than just adding up Ci to G square, it's the weighted average of Ci and G square. There's a weighting term, delta. You get the previous gradients times delta, the previous gradient square times delta. This is Ci minus 1. I'll write it again. Delta times Ci minus 1 plus 1 minus delta times something like that. So you get delta amount of Ci minus 1 and 1 minus delta amount of the current gradient that controls the learning rate. So more recent examples contribute more to this expression that controls the learning rate. At this point, it seems a little tedious, and it should. If it does not, then you're lying. I think RMS prop does not have a paper for it. If memory serves me right, the official citation for that is a certain class lecture that Jeff Hinton had in a machine learning class around 2010 or 11. It's just the official citation is lecture number 12, Introduction to Machine Learning, Jeff Hinton, or something like that. Anyway, people use that, and it allows for stability of learning. All of these things have allowed for learning to be more stable. The key point here is for all of these, we still have to compute the gradient. To compute the gradient, we still use backpropagation. So let's take stock of all the gradient tricks we have. Momentum allows you to use a smooth weighted average of all the gradients so far, so that you smooth out the gradients. ADAGRAD and RMS prop have this idea that you have an adaptive learning rate for each parameter, and that's different from that changes based on how the gradients work. These two things are independent of each other, right? I could have a weighted average of the gradients and an adaptive learning rate. Well, if you put those two together and add a little bit more secret sauce, you get something called ADAM. ADAM is a combination of a whole bunch of ideas. ADAM uses momentum for smoothing the learning rates. It uses RMS prop for adaptively choosing the learning rate. There is some well-motivated, but a little bit more technical pieces to ADAM that are there to avoid statistical biases that happen at the beginning of learning. I'm not going to go into that, but you can look up the paper. And today, when people use gradient-based optimization, for the most part, they use ADAM. They use ADAM or some minor variant of ADAM, but for the most part, that's what it is. And ADAM has a whole bunch of hyperparameters. There is the initial learning rate. There is this alpha that I did not talk about, but it's there. There is this delta, which talks about how much of the GI should influence, how much of the older gradient should influence the current learning rate. And then there's also the mixing term that showed up for momentum, which is this expression here, this mu. ADAM has a whole bunch of hyperparameters, and I think, fortunately, the defaults in the neural network libraries are, for the most part, good. So we don't have to necessarily do hyperparameter tuning across all of these, because I think we'll never see the end of it. Questions? Yes.
For momentum, how do you know about V zero, like the first?
You set it to 0. Yeah, you set it to 0. And that's actually related to this thing here. Adam has a few interesting tricks to make sure that those estimates are unbiased. But basically you can set it to 0. Setting it to 0 introduces a certain bias. And that's the thing that I kind of brushed aside right now. Other questions? Let's now talk about another point, which is overfitting. You know, for a good part of the semester, I talked about how simplicity is a virtue. Simpler models are better because they don't overfit. Use simpler models because of Occam's razor and such things. And then in neural networks, we have this ability to construct incredibly complex functions. So neural networks, if you have a large enough model and you run it for long enough, there's a good chance you will overfit. And that's obviously a bad thing. There are a few approaches to address that. One common approach is to use a holdout set, a validation set whose examples are kept aside from the training data, and you train your model on the training data. And after a certain number of updates, you check the performance on this holdout set. You essentially would get a plot that looks like this. This is number of updates, and this could be validation performance. Let's say higher is better in this axis, and maybe it goes down, and then after a certain point, this curve starts going up. That suggests that you should have stopped training right there. And this is commonly done. You basically keep track of validation performance, and when it starts getting really, really bad, or when it starts getting worse, you stop training and you take the model that had the best validation performance. Or you could run it all the way through and then come back in time and then take the checkpoint. You checkpoint all the models and you take the checkpoint that did the best. Basically, you maintain the weights of the best performing model and you return those become the solution rather than the one that minimizes the objective value. Yes.
Imagine the neural network libraries where now we have the tools necessary to save our model.
Yes.
These steps.
Yes. It's called model checkpointing. Absolutely, yes. But that should not be a cause for too much comfort, because these models are so large that if you checkpoint all of them, you run out of hard disk. So then you have to figure out how much you want to checkpoint and such things. Anyone who tells you that modern machine learning is going to get rid of programming, I challenge you to build a modern machine learning system, because there is so much systems and so much computer systems and computer programming that goes into it, which is just incredible. All the lessons from the entirety of computer science show up here. Anyway, that's a conversation that we can have, that I can talk a lot about, but I don't want to right now. There's another problem here, though, but that if you start using a validation set, that means that you're not able to train on that data. You lose some data to validation. And one answer to that, mathematically correct answer to that, is you can use k-fold cross-validation. K-fold cross-validation is a fantastic idea until you realize that you have to train k models. If training one model takes a month and costs $1 million, then k models costs k $1 million. So lately, I don't see this in the literature. But still, we haven't addressed the problem of overfitting. And that takes us to something called dropout. Dropout was an idea that was essentially invented for neural networks, and it's an important idea because it almost marks this shift between when neural networks became useful and when they did not. Before this was introduced in 2012. Imagine that you have a neural network. And let's say during you're performing training, you have a mini batch right now, and you need to compute the loss. The idea of dropout is that you randomly create a mask and you say that some neurons, like these crossed out things there, are inactivated in the forward pass. Actually, they are inactivated for this batch. Imagine that these nodes do not exist. So only 4 nodes exist, and the model has to make the right prediction using only those 4 nodes. You compute the loss, and then you make the update only on the weights that touch those 4 nodes. Importantly, you don't make any updates to those inactivated, to any weight that touches an inactivated node. So essentially, you have dropped out some of the nodes in that neural network for this particular mini batch. And then you toss out the mini batch because you're done with it. Then you get a new mini batch. You create a new dropout mask. You randomly choose some nodes to inactivate. They may be the same nodes. They don't have to be the same ones. So essentially, you have a hyperparameter now called dropout ratio. Some p fraction, or you delete a hidden unit with some probability p. You don't delete it, you basically mask it with some probability p, and then you want the rest of the neural network to be able to make the prediction without these, without these masked nodes. And you only make updates to the nodes that are active in this batch. And you keep doing this. Essentially, you randomly choose subsets of the neurons to update, subsets of the weights to update at any point. This tends to avoid overfitting. And this is the standard method for avoiding overfitting with neural networks today. Compare this to the other approach that we saw for avoiding overfitting. We saw regularization. You don't see a lot of regularization with neural networks today. Instead, this serves as the sort of a procedural mechanism for regularization. And there have been some attempts to explain why this works. One idea which I find sort of intellectually satisfying is that this allows the neural network to be robust. It allows certain parts of the input, certain parts of the network to independently be able to make the right prediction without the others being involved. And when a new example comes in, maybe only some parts of the network are actually activated by that new example because it looks different enough from the training data. And so it has this effect of making the model more robust. In the same way, or not in the same way, but in sort of a similar way that an ensemble does. Here we are creating this ensemble on the fly. Different parts of the network are activated for different examples, and all of them have to kind of converge to be, all of them should independently be able to produce the right answer. This is a very hand-wavy explanation for why it works. There are some instances, some attempts to explain dropout more formally. And there are even attempts, there are some papers that I'm aware of that show that dropout is it behaves as if you had a certain regularizer, but you didn't use it. But to be able to prove that, there are enough assumptions along the way that it doesn't explain the phenomenon in general. But that's another hyperparameter. So when we see papers with neural networks, usually there's a big table at the end of the paper that says these are our hyperparameters. One of them is dropout ratio. People try out a few different dropout ratios and they pick one. And how do you know which one to pick? Well, you use a validation set again. You use the one that gives the best validation accuracy. Questions? Yes.
When I'd heard of dropout before, I'd heard of it being explained as a way to make it so that the neural network is perhaps less dependent on certain neurons
Yep.
to provide information. Is that kind of like the model averaging?
Yeah. Exactly. I mean, there are multiple independent ways of producing the answer. And that way, if any one of them becomes irrelevant because of this new example having certain, the new example being one that's not from the training data, having certain idiosyncratic properties, the other paths to the answer will still exist. So that's what I mean by model averaging. There are multiple ways to get to the answer, and the final answer is aggregated across all of them. This is just a loose and hand-wavy explanation. I mean, it's not a mathematical statement. I have seen comparisons between Dropout and this book called Anti-Fragile, which I thought was a very out there comparison. There are multiple attempts to explain it. But yeah, there's a question on Zoom. Can we use cross-validation for to avoid overfitting on neural networks? Nothing prevents you from doing that except computation. Cross-validation is a statistically valid estimator of the hyperparameter values, except at this point, if you notice, we have so many hyperparameters that cross-validation is going to become extremely expensive. So increasingly, I'm seeing less of that in the literature. We just see validation sets, and some hyperparameters are chosen just by conducting small experiments on small data and getting trends and saying that, yeah, this hyperparameter, this range seems to be good. I'm going to use that and scale it up. It becomes a bit of an art. Cross-validation is correct, but becomes expensive. I saw a few other hands. Yes.
What is the basis that we use for deleting that?
You don't delete a hidden layer. You delete weights. And it's well, you can also use delete hidden units. It is randomly with some probability. You create a random mask that masks out all the irrelevant, all the ones that a mask is just think of it as a matrix with zeros and ones, and you multiply that with the weights in this current forward pass. And by doing that, only the weights that have a 1 are going to propagate forward and propagate back. And the ones that are 0 are inactivated, and every time you create a new random mask. In practice, you don't do any of that. In practice, what you do is you initialize your optimizer in PyTorch and you say dropout ratio is 0.5. And that does the whole thing internally. Yes.
Do we need to recompute our partial derivatives for each step?
What do you mean?
I guess when we're not using dropout, right, we do the back propagation.
Yes.
We calculate our partial derivatives for each neuron, right?
Yes.
We store those in memory.
Yes.
I imagine that if we start deactivating neurons or nodes, that those partial derivatives would change.
No, they won't. So they're not going to change with respect to this mini batch, because what you create the mask at the beginning of the mini batch and you freeze it till for the duration of this mini batch. So I'll give you a simple example. So let's say that we have that tiny neural network that we saw, so with just these 4 things and maybe this thing here. Okay, so how many weights do we have? We have, I'm going to call this W11, W12, this is 1, 2, 1, 2, and this is Y. This is W21, this is W22. Let's pretend that the top layer weights are frozen. We're not going to worry about that. Let's just look at this one. These weights, I can write it as a matrix. And when an example comes in, let's call this X1 and X2, I'm essentially multiplying this with this vector here. That's my forward pass. Now, what dropout does is it creates a mask. Let's say the dropout mask looks like something like that. That means you are, before you do anything, you multiply element-wise these 2 matrices, which means W11 gets zeroed out. Let's say we do that. Let's say it gets zeroed out. And you just compute the forward pass. Because W11 had a value 0, the gradient will also, everything gets zeroed out. And sometimes for odd cases where things are a little bit uglier, you might actually multiply the gradients with the same mask. But you still store the partial derivative, and everything just works out exactly. You pretend as if, essentially what this is doing is you pretend that this edge did not exist. And now the network has to make the prediction without that edge. If that edge did not exist, we still have a computation graph. Everything else still applies. I realized that in the slide before this, I talked about you randomly mask out hidden units. There are 2 variants of dropout, and I don't remember which of those is implemented in the libraries. I think it's this one where edges are masked out. But the same, when edges are removed, the idea of backpropagation still is the same. Okay, another practical issue is how big should your network be? If you have too many hidden units or too many hidden layers, then you're going to overfit. If you have too few hidden units or too few hidden layers, your representations that your model computes along the way are not going to be good enough, and your model will underfit. It's not going to be expressive enough to represent the concept. A very extreme example of that is if you have if you have 0 hidden layers, it's basically a linear classifier, you can't represent things like XOR. So that's called underfitting. Your concept class is, your concept is it's outside the set of functions that your hypothesis class can express. And how do you handle that? Well, this becomes you treat it as if it's a hyperparameter. You try out a few different architectural variants and use a validation set to find the best one. Of course, you can't do exhaustive search because that's an infinite problem. You are limited by how much your tools allow you to do, namely your compute. Okay, I'll start wrapping up. In these last 3 lectures, we saw what neural networks were. And one sort of a intellectually satisfying way to think about neural networks is that they are functions that learn representations of data so that subsequent layers can adequately represent a concept. Because of this, they are highly expressive, and you have to think about whether high expressiveness is always a good thing, because extremely expressive functions also tend to overfit. Neural networks have seen an explosion in the last decade and a half because of the large amount of data that we use, but also because of the backpropagation algorithm being super efficient at computing gradients without actually knowing what the function is. Backpropagation that was implemented in PyTorch several years ago can be used for training a neural network that will be invented a decade from now. The person who implemented backpropagation did not need to know the architecture of the network that you are going to use. And that allows us to kind of explore various new architectures in interesting ways. We saw only 3 lectures of neural networks. Unfortunately, this is a very, very vast area that keeps moving fast. There are many new models that keep getting invented all the time. There are new algorithms and new kinds of optimization tricks that show up, new interpretability tools. The area moves fast with data, with respect to algorithms, with respect to all the sort of folk knowledge and tricks that are necessary for training. And of course, the models themselves keep getting bigger. The data sets keep getting larger. And along the way, we have named neural networks that allow us to essentially play Lego with building blocks. Different types of problem domains can naturally support different types of neural networks. Early on, around 2010-ish, there was or maybe 12, there was a lot of people working on something called restricted Boltzmann machines, which actually is historically, it goes back to the 1980s, and autoencoders. And the idea was, can you learn a good feature representation of the data using a neural network by having a network produce a latent representation and then forcing another network to reconstruct the data from it. So it encodes the data and along the process learns the representation. And these representations could be used for something else. Convolutional neural networks, which were actually modeled after biological neural networks that are in mammalian visual cortices or cortexes, I'm not sure. These are the de facto systems for computer vision tasks when your inputs are either images or 3D versions of images and such things. Convolutional networks almost were the first poster child of neural network success in 2011. If your data looks like a sequence of things, a sequence of words, or a sequence of audio signals, then the default building block here is something called a recurrent neural network. Increasingly though, the default building block for sequences is something called the transformer neural network. Transformers are the architecture that power things like ChatGPT. There are many things here, and we did not cover all of these. If you're interested, there's an entire class on deep learning that you should be looking at. All right, we'll stop here. We are a minute over time, so I shouldn't keep you here. In the next lecture, we'll be looking at more practical issues with machine learning.